Welcome to Signal Ahead. I'm Alfred. Today's briefing, quantum computing, Thursday, July 9. This is the synthesis above the noise, not the headlines, but the deep currents beneath them. Let's get into it. Here's a question worth sitting with before we go anywhere else. If you wanted to know how healthy the field of quantum computing really is, not the press release health, the actual health, where would you look? The instinct, the casual reader's instinct, is to look at the qubit count. How many qubits does the new machine have? 104? More? That number gets the headline, and it feels like the score in a game we all vaguely understand. Bigger is better, and whoever has the most is winning. I'd like to suggest that the qubit count is very nearly the least interesting thing happening right now, and that the real story is hiding in a phrase most people would scroll straight past. The phrase is mid-circuit measurement. A collaboration between physicists in Sydney and the team at IBM spent their effort not on adding qubits, but on quantifying and then mitigating a bottleneck that appears when you try to measure a qubit in the middle of a computation rather than at the end. Now, why would you ever want to measure in the middle? Because that is precisely what fault-tolerant quantum computing requires. Error correction is not a matter of building perfect qubits, nobody can, and the laws of physics are quite firm on the point. It is a matter of constantly checking your qubits mid-flight, detecting errors as they creep in, and correcting them without collapsing the very computation you're trying to protect. That mid-circuit measurement is the heartbeat of the whole enterprise. And it turns out the heartbeat has an arrhythmia, a hardware engineering bottleneck that had gone properly unquantified until now. Here is the cross-cutting insight, the connection the news cycle misses. The field has quietly stopped being about how many qubits you have and started being about how well you can measure and control the ones you already possess. Read across everything happening this season, and the same theme surfaces again and again in disguise. A single ion at ETH Zurich mapping electromagnetic fields above a chip in 3 dimensions with record sensitivity. That is a measurement and control story, aimed squarely at making better quantum chips. A Finnish company drawing serious investment not for qubits, but for cryo-CMOS control and readout microchips, the unglamorous silicon that sits beside the qubits and tells them what to do and listens to what they say. A Korean institute building a single photon source that runs at room temperature in a rack-mounted box, moving a delicate quantum light source out of the cryogenic laboratory and towards something you could actually plug in. Even the Max Planck work showing you can recover the entangled properties of light after almost all of it has been lost on the way to the detector. That, too, is fundamentally about measurement surviving contact with a hostile, lossy world. So the field center of gravity has shifted from the qubit to everything wrapped around the qubit, from the star of the show to the stage crew, and that shift tells you something rather encouraging about maturity. Young fields chase the headline number. Maturing fields discover that the headline number was never the constraint, that the real limits live in the plumbing, the wiring, the readout, the moment of measurement. When your best minds start publishing papers on bottlenecks nobody had bothered to measure, that is not stagnation. That is a field learning where its actual problems live. There's a second thread I want to lay down now, because it runs underneath the whole argument to come. Alongside this deepening of the engineering, the money and the institutions are moving as if the destination were already assured. A European hardware maker debuts on an American stock exchange with the better part of $400 million in the bank. Another company files to go public while simultaneously working through a merger. Series B rounds close, oversubscribed. Shanghai stands up 2 quantum districts within days of each other. India prepares to switch on one of its first physical machines. Cloud programs pool processors from rival vendors to put real quantum hardware into 40 universities' classrooms. There is an entire apparatus being built, legal officers hired, foundries opened, national testbeds funded for a technology that, by the measurement of its own most honest researchers, still can't reliably check its own work mid-computation. That is the tension I want to hold up to the light across this conversation. On one side, a science growing more honest and more granular by the month, cataloging its own bottlenecks with admirable rigor. On the other, an economy and a geopolitics behaving as though the fault-tolerant machine already exists, and it's merely a matter of shipping. Neither picture is wrong, but they are not the same picture, and the gap between them is where the interesting risks and the interesting opportunities both live. So that's where we stand, not at a finish line and not at a dead end, but at the point where a field stops asking how big and starts asking how good, how controlled, how correctable. While the world around it places its bets, let's look next at what the science itself is actually telling us. There is a particular temptation when surveying a field as loud as quantum computing has become to fix one's attention on the biggest number in the room, a machine with more qubits, a funding round with more zeros, a stock ticker making its debut on a major exchange. These are the headlines, and they are not nothing. But if you listen only for the loudest sounds, you will miss the deep current, the slow, structural movement beneath the froth that actually determines where all this is heading. And so let us do something rather unfashionable and pay attention to the quiet parts. Consider a collaboration that set out not to announce a triumph, but to measure a bottleneck. A team examined, with some care, the problem of taking a measurement in the middle of a quantum circuit, reading out 1 qubit, while its neighbors must carry on their delicate computation undisturbed. This is not glamorous work. There is no headline number attached to it, no qubit count to boast of. And yet mid-circuit measurement sits at the very heart of fault-tolerant computing because error correction depends upon it. You cannot fix a mistake you cannot see, and you cannot look without risk of disturbing what you're looking at. To isolate that bottleneck, to quantify it, to begin to mitigate it, that is the deep current. The field is turning slowly and in earnest, from the question of how many qubits one can build toward the far harder question of how well one can control them. Notice how much of the recent activity, once you strip away the announcements, is really about control and readout. A Finnish hardware developer securing investment specifically for cryogenic control chips, the humble silicon that sits beside the quantum processor and tells it what to do. A single ion being used to map electromagnetic fields above a chip's surface with record sensitivity, precisely so that future chips might be built with fewer of the stray disturbances that ruin computation. A method for observing the quantum properties of light, even when nearly all of that light is lost before it reaches the detector. None of these will trend on any exchange. All of them are load-bearing. The structural trend is that the frontier has quietly relocated from the qubit itself to everything surrounding the qubit, the plumbing, the wiring, the measurement apparatus, the packaging. And here is where the deep current becomes visible in the economics. Watch where the money is actually flowing. Not only into the marquee processor makers, but into photonic integrated circuit packaging, into thin-film lithium niobate foundries, into control and readout microchips, into single-photon sources you can mount in a 19-inch rack and switch on without cryogenics. This is the signature of an industry beginning to build a supply chain. When a technology is young, everyone tries to do everything under one roof. When a technology is maturing, it begins to specialize, a foundry here, a packaging competency there, a control electronics firm somewhere else. Specialization is not a symptom of fragmentation. It is a symptom of confidence. Firms only carve out narrow niches when they believe the whole will hold together long enough to reward the part. There is a second current running alongside the first, equally quiet, equally telling. Watch the geography. Consider the deliberate construction of dual quantum districts in one Chinese metropolis, the commissioning of physical machines in a greenfield Indian city, a European hardware firm listing on an American exchange, while a South Korean ministry stitches together alliances with Canada, the United Kingdom, and the European Union, all against a backdrop of tightening export controls on the deep tech materials this whole enterprise depends upon. The pattern beneath the announcements is that quantum computing is being reconceived by states as strategic infrastructure, not as a product to be purchased, but as a capability to be sovereignly held. That reframing changes the incentive structure entirely. It means funding will persist through the disappointments because the thing being funded is no longer merely commercial. It is national. And a third current, subtler still, the quiet cultivation of people. Pooling processor time across 40 universities so that undergraduates might touch real hardware. Merit-based programs handing free machine time to tenure-track faculty. This is a field investing in a workforce it does not yet need, for machines that cannot yet do the thing they are ultimately for. That is not the behavior of a bubble. A bubble spends on spectacle. This is spending on foundations, on measurement, on supply chains, on sovereignty, on people. So the deep current, beneath all the noise, runs in one direction. The center of gravity is shifting from demonstration to durability, from the qubit to its entire surrounding apparatus, from a race to a build-out. When we return, we shall ask where that current is carrying us and what could yet divert it. So we've spent our time together looking at the machinery, the mid-circuit measurement bottleneck, that a collaboration between Sydney and IBM managed to isolate and mitigate, the hadronization simulation running across 100-odd qubits, the room temperature single photon source tucked into a 19-inch rack. Now comes the harder question, the one that these announcements never quite ask of themselves. What does it all mean, downstream, once the excitement of the press release has cooled? Let me offer you the first observation, and it's a slightly counterintuitive one. The most consequential progress this season isn't in qubit counts. It's in the unglamorous plumbing. Consider what it actually means to quantify a mid-circuit measurement bottleneck. Measuring a qubit partway through a computation, reading it out without disturbing its neighbors, is precisely the operation that error correction depends on. You cannot have fault tolerance without it. And for years, this was a known problem spoken of in hand-waving terms. To move from "this is hard" to "here is the specific mechanism, isolated, and here is how we blunt it," that is the difference between complaint and engineering. Watch for this pattern everywhere. The field is quietly shifting from demonstrating that something is possible to characterizing exactly why it's difficult. That's a maturation signal, and it's far more reliable than any qubit tally. The second implication concerns where the value is pooling, and it's not where the marketing points. Notice how much of the recent activity is about control and readout electronics, photonic packaging, cryogenic chips, a Finnish firm scaling cryo-CMOS control chips, a Swiss foundry expanding thin-film lithium niobate photonics, a Canadian center of competency devoted entirely to photonic integrated circuit packaging. None of this is the qubit itself. It's the layer around the qubit, the interface between the fragile quantum object and the ordinary world of wires and computers. And here's the second-order thought: whoever owns that interface layer may end up owning the economics of the entire industry, regardless of which qubit technology eventually wins. It's the picks and shovels logic, but applied to a domain where the shovels are genuinely difficult to make. If you want to know who prospers from quantum computing, don't watch the qubit races. Watch the packaging houses and the readout chip foundries. Third, and this is where the geopolitics enters. The pattern of national investment tells you the story has changed character. Shanghai stands up 2 quantum districts in a single week. India commissions physical machines in a greenfield city. South Korea convenes a dozen countries and turns an exhibition into a diplomatic instrument, explicitly framed around tightening export controls on deep tech materials. That phrase deserves attention: export controls on materials. It signals that governments now treat quantum not as a research curiosity, but as strategic infrastructure, the way one might treat semiconductors or rare earths. The second-order effect is fragmentation. We may be watching the early formation of quantum blocks, each with its own supply chain, its own alliances, its own walled garden of talent and hardware. That's efficient for national security and rather corrosive for science, which has always thrived on porousness. Keep an eye on whether the collaborations we saw Sydney with IBM, a Berkeley researcher on IBM hardware, survive the hardening of these borders. If the cross-border work thins out, that's your signal that the blocks are setting. Fourth, the money is behaving in a telling way. A European hardware maker listing on Nasdaq with $1/3 billion in cash. Another firm filing to go public while a merger is still in motion. Series B rounds closing oversubscribed. The capital markets have decided quantum is investable now before the machines are useful in any commercial sense. That's a gamble on timelines, and gambles on timelines have a way of curdling into disappointment. Watch for the gap between what the balance sheets promise and what the physics delivers. If fault tolerance remains 3 to 5 years out, as it perennially does, some of these public valuations will meet reality unpleasantly. The prudent observer holds 2 thoughts at once. The science is genuinely accelerating, and the financial expectations may be running ahead of it. And finally, the quiet one. Post-quantum cryptography is being deployed on live systems right now, a full standards-compliant stack running on a public blockchain, quantum-safe partnerships spanning continents. This is the world defending against a machine that does not yet exist. It sounds absurd until you remember the harvest now decrypt later problem. Adversaries can store your encrypted secrets today and crack them the moment a capable machine arrives. So the defense must precede the threat by years. That inversion, building the shield before the sword is forged, is perhaps the strangest and most honest thing about this whole domain. So what to watch? Not the qubit counts. Watch the interfaces, watch the borders, and watch the gap between capital and physics. The signal, as ever, is in the plumbing. That's the signal for today. The noise will keep coming, we'll keep finding what's underneath it. This has been Signal Ahead with Alfred. Until next time.